So, welcome back to this NPTEL lecture on friction and wear of materials. In last few lectures, I have discussed some of the case studies to explain the nature of friction and wear properties of metals and ceramics in cryogenic environment, and cryogenic means more particularly liquid nitrogen environment and under high speed sliding conditions. This is the last lecture on the cryogenic wear of materials, and in this lecture I will describe one more case study again from our own research, and that is on silicon carbide ceramics. Now, silicon carbide and silicon nitride, these are the two non-oxide ceramics which has received wider attention, particularly for high temperature applications. And silicon carbide and silicon nitride, these are also used as the ball bearings in as ball bearings, because you can shape them to a balls of different sizes. So, it was interesting for us to understand and investigate the sliding wear of silicon carbide in cryogenic environment with an objective to assess their suitability for ball bearings in space shuttle main engines. So, this was the background. So, as I have categorically mentioned in one of the earlier lectures, that 440C martensitic stainless steels or 304C stainless steels, they are mostly sought material currently used for ball bearings in space shuttle main engine. And under high speed sliding conditions, high friction and wear of unlubricated bearings can be tolerated, but it severely curtails the overall life of the bearings. And then in some of the earlier lectures, I have mentioned that how the cryogenic wear properties of these two oxide ceramics, one is that alumina and another one is zirconia, how they are different from their room temperature sliding conditions. So, here we would like to again address the similar issues that I have posed while discussing the earlier case studies, and those are whether liquid nitrogen serves as coolant or lubricant, and what would be the influence of liquid nitrogen on frictional and fracture behavior at sliding contacts, and how does the material removal process occur in liquid nitrogen environment, and how does the change of environment room temperature to liquid nitrogen modifies the friction and wear properties of alumina. Similar to earlier case studies, here we have varied the sliding speed from 0.67 meter per second to 1.1 meter per second, and load, if we keep the load at 5 Newton, we have found that coefficient of friction is around 0.38, so around close to 0.4, which is relatively higher compared to some of the metals. And Hurrian contact stress is 1.2 gigapascal, mean average Hurrian contact stress was 0.8 gigapascal, and flash temperature is at 0.67 is sub-zero temperature, at 0.89 is 47 degrees Celsius, and 1.1 meter per second it is more than 100 degrees Celsius. And flash temperature was calculated according to the equations that I have described at greater details in one of the initial lectures in this NPTEL lecture series. And flash temperature also we calculate in the room temperature environment. Now, this is how the coefficient of friction evolves with time for the tests that we have conducted up to 10 minutes, that is up to 600 seconds. So, what you see here, that this coefficient of friction goes of very high value, and then it goes through some kind of unstable region, and then finally it reaches the steady state after the 5 minutes, and then it gets very much flattened. And if you compare the steady state coefficient of friction we do not see much change because it varies over the window of 0.3 to 0.4, but there is lot of undulations there. If you look through this very closely, that frictional behavior of self-melted silicon carbide. How about frictional behavior of self-melted silicon carbide? That means silicon carbide versus silicon carbide. So, here the flat materials is silicon carbide and ball material also silicon carbide, and under the similar sliding conditions with variation in speed from 0.67 to 1.1 meter per second and the load is around 5 Newton, we see not much difference in terms of the steady state coefficient of friction. Only thing is that in room temperature conditions, that this couple reaches the steady state at a much earlier time scale of up to 3 to 4 minutes, but whereas in liquid nitrogen we see lot more unstable region in the frictional behavior. So, if you go back to this particular table where these things are kind of fill in the blanks, and you can now fill in the blanks because there is not much difference in terms of the steady state coefficient of friction between room temperature and liquid nitrogen tests. Now, as far as the quantitative data on the wear resistance is concerned, this is the results we have obtained in liquid nitrogen environment based on the laser surface profilometric analysis of the sliding track. What we got, that wear depth is fairly small. So, wear depth is less than 0.4 micron. Okay. This is the wear depth, and wear depth decreases as you increase the speed, and it reaches almost like a steady state value of around 0.1 micron. As far as the wear rate is concerned, it is 10 to the power minus 6 millimeter cube Newton meter, and again it changes from 3 10 to the power minus 6 to less than 1 10 to the power minus 6 millimeter cube per Newton meter for self-melted silicon carbide at 5 Newton load. So, less than 0.4 micron depth at such a high speed sliding conditions and under high contact stress is really a good number. So, what I point out here that it is 3 into 10 to the power minus 6 goes to less than 10 to the power minus less than 1 into 10 to the power minus 6 means that once you go down the scale here, so here you can approximate as millimeter cube per Newton meter. So, essentially what I am trying to point out here, that it is possible to decrease the wear rate by 1 order of magnitude, or it is possible that self-melted silicon carbide can experience 1 order of magnitude less wear rate at higher sliding speed of 1.1 meter per second compared to that what the self-melted silicon carbide experiences at 0.67 meter per second. So, all in all, there is wear rate and wear depth, both the data, if we consider together, it really leads to the conclusion that self-melted silicon carbide experiences very high wear resistance or less wear rate in liquid nitrogen environment. Now, if you look at that similar data of wear rate and wear depth after self-melted silicon carbide are slided at ambient conditions, that is room temperature, and this is that wear rate that was measured on the silicon carbide flat. And what you see again, that this wear rate decreases, and almost like linear fashion as we increase the sliding speed from 0.67 to 1.1 meter per second. The same is true for the wear depth, but both the numbers here, if you compare to the liquid nitrogen conditions, sliding conditions, because both the y scale are the same, if you notice here, and if you compare now the y scale values, then you are convinced that room temperature sliding conditions leads to more wear of the self-melted silicon carbide. under these particular sliding conditions on a pin on disc tribometer. So, there is a very clear signature that wear resistance on a hole or as a combination of wear rate and wear depth is much reduced in liquid nitrogen sliding conditions compared to that under ambient condition. Now, this is the typical 2D surface profiles what we have measured in laser surface profilometer. LSP stands for laser surface profilometer. So, you have the sliding speed like 0.67 meter per second to 1.1 meter per second, and you can see very clear sharp peaks and valleys in the 2D surface profile. What it means is that these are the signatures of the differential wear. That means this wear profile or 2D surface profile is not very smooth, and it shows multiple surface groups of different heights and also different shape. So, essentially these are the signatures of the differential wear behavior. Now, if you look at this scanning electron microscopy images, so this is your sliding track and this is your sliding directions. And if you look at little bit closely, if you look at this particular region, so there is some contrast difference showing that perhaps some of the silicon carbide can be oxidized to silica. Let us look at much more details into what is happening at intermediate sliding speed of 0.89 meter per second after the sliding is over for 10 minutes. Okay. So, this is your sliding directions, and if you look at this particular region or this particular region, here you can clearly see this backscattered electron image. It appears with different contrast compared to this particular region of the sliding surface. So, that means the tribochemistry plays a role, and also there is tribochemical reactions that is taking place under these sliding conditions at 0.89 meter per second. This is at the high sliding speed conditions, and you can see this is your wear track, and this wear track, a closer look at this particular region clearly shows you that there are multiple or there is numerous micro cracks. So, this micro cracking is playing an important role in this particular case, and that is a high sliding speed of 1.1 meter per second. Unlike this alumina or zirconia, in silicon carbide we have fixed the normal load of 5 Newton, but ideally using the same tribometer one can do the experiments with variation in the normal load. But here we are more interested to understand that if you increase or if you vary the sliding speed over similar window, what would be its influence on the wear resistance and wear mechanisms of self-melted silicon carbide rather than load dependent wear behavior of self-melted silicon carbide. So, you will see that similar behavior at 1.1 meter per second at some part of the tribo layer, and you can see this is the region where it clearly shows that this particular region should have different chemical composition or different chemistry compared to this particular region. So, this region certainly is very rough, and this roughness of this wound surface can be attributed to cracking and localized spalling from the tribo layer. So, this is even that higher sliding speed of 3.3 meter per second at 10 Newton load, and here again we have done the experiments up to 1200 seconds. So, 1200 second means up to 20 minutes. So, we cannot do one of the things I think I might have mentioned in the earlier lecture, that there are two major difficulties with using this cryogenic sliding wear experiments. The first one is that with this tribometer it is extremely important to fix or place the ceramic disc inside the tribometer in a very stable manner. If there is certain difference in the top surface or the leveling of the surface, then what would happen, ceramics being brittle materials, when it will experience high sliding speed against the ball, when ball is stationary and then disc is rotating, there is every chance the ceramics disc will be broken into two pieces. But here we are more interested to know how does the ball behave. It is not about the disc, but in the ball, but to have the self-mated conditions, essentially we are trying to understand that under the self-mated conditions, when the ball will be slided against the same material of similar composition, what would be the influence on its friction and wear behavior. So, from that point of view, we have conducted all these experiments. So, the first difficulty is that placing the ceramic disc, and that is very important. Second one is that we cannot carry out this high speed sliding wear experiment in a cryogenic environment for up to longer time period, like up to 30 minutes continuously, because it causes lot of undulations, and because of the high speed sliding conditions. And in the space shuttle main engine also, as far as the bearing life is concerned, the 440C martensitic stainless steel bearing ball used to have a life of less than half an hour. So, if we can do these tests up to 20 minutes or so on, that is good enough for these particular applications in mind. Now, coming back to this particular scanning electron microscopy images, again you see this large region here, it is a tribolayer, and also here, and if you blow up this particular region, some of the region you can focus, then you can see that there is a very thin tribolayer which is covered on this individual silicon carbide grain. Okay. So, essentially these are the places where silica rich layer perhaps have formed. So, 3.3 meter per second indeed is very high sliding speed, and under these conditions the only way that the silicon carbide is worn out, it is because of the grain boundary cracking. And you can see that at various locations like these locations as well as these locations, there are small micro cracks which are found, and this presence of this micro cracks essentially indicate the occurrence of the intergranular cracking. The same is true for little bit higher magnification ACM images, just to illustrate that how this silicon carbide wear is influenced by high speed sliding conditions. So, this is that one arrow, and this is the another arrow. As you can see that these are cracking also it shows, and also there are small pockets of the pull out region that you can clearly see here in the on the own tribological surface. And also you can see this is the layer of the tribolayer, and this is again in the region that where the micro cracks takes place. So, what you have seen earlier in case of alumina and zirconia, and what you see now in case of silicon nitride, I am sure that you would agree with me that sliding wear of silicon carbide is governed by more tribomechanical wear and partial tribochemical wear. If the tribochemical wear would have played a major role, then entire tribolayer would be covered with the tribochemical layer, and that is certainly not the case. Second thing is that despite the dominance of the tribomechanical wear, what you see the tribo surface is relatively smooth, not extremely rough, what we have seen earlier in case of alumina, particularly in case of the alumina, which is again a model brittle ceramic. Now, if you go back to now, if you look at the where at the grain level or the grain scale, now if you see this is the two silicon carbide grains which is tabular in nature, and you will see that this this region is again another region where you can see cracks. So, there is micro cracks, grain boundary cracks, and these cracks sometimes goes deep into the material. So, this cracking is taking place, but the cracks are getting deflected around the grain boundary region. And if you look at the crack deflection along the grain boundary region, so essentially that crack deflection leads to delayed wear in case of silicon carbide. So, if the grain boundaries are the paths for the crack propagation or the crack deflection, certainly it will help in increasing the wear resistance of these materials. So, this is what we have seen at 3.3 meter per second for 20 minutes of the sliding speed. Now, if one look at the, if we compare, this is fairly an important slide. So, let us spend some time in comparing the numbers which are placed in this slide. So, in last two lectures we have seen that self-melted silicon alumina, self-melted zirconia. In this lecture I have described the wear behavior of self-melted silicon carbide. Now, if you want to be extremely fair in making this comparison, it is important to fix the load, because the load is varied in these three studies, but one load is very common for alumina, zirconia and silicon carbide, that is 5 Newton load. And a 5 Newton load, depending on what is the kind of elastic modulus of the materials, that leads to difference in the Hertzian contact stress. For example, oxide ceramics, their elastic modulus is relatively lower compared to silicon carbide. So, therefore, in the oxide ceramics here, like alumina is 390. So, their gigapascal is the elastic modulus. So, this is the elastic modulus value I am talking about. Zirconia is 210 gigapascal and silicon carbide is little higher than alumina also. So, 5 Newton load, it leads to 1.2 gigapascal as the maximum Hertzian contact stress, which is 0.78 in case of alumina and which is 0.49 in case of zirconia. Now, typically the wear rate in case of alumina is around 10 to the minus 10. In case of zirconia it is 10 to the minus 4, 10 to the minus 4 and 10 to the minus 10, and in case of silicon carbide is 10 to the minus 7. So, if you look at that wear rate, alumina is certainly highly wear resistant, or 10 to the minus 10, followed by silicon carbide 10 to the minus 7, and zirconia is least wear resistant at 10 to the minus 4. Zirconia also experiences a high coefficient of friction, about 0.5 to 0.75, whereas silicon carbide, the coefficient of friction is around 0.38. Alumina, it is the lowest. So, looks like alumina is the better wear resistant materials as far as the cryogenic sliding conditions. Remember, all this data that we have summarized in this table are obtained under liquid nitrogen sliding conditions, not like not in the room temperature. However, only one point that I must note here, that wear depth wise alumina has larger wear depth 5.5, whereas silicon carbide is 0.1, extremely small, and alumina and zirconia is relatively similar, like 5 to 5.5 micron. So, 5 micron versus 0.1 micron, it is a order of magnitude difference, right. So, I just what I wanted to compare these two values, 5 versus 0.1, it is order of magnitude difference in the wear depth. So, therefore, what I believe that if you compare these two, like say 10 to the power minus 7 and 0.1 micron wear depth, looks like silicon carbide is not a bad choice either. So, therefore, what I believe that although alumina is a good choice, but silicon carbide is also equally the second choice. So, number one choice is alumina, number two choice is silicon carbide. And we have also established a close correlation between the wear mechanism and the wear rate, and where we have found in self-melted silicon carbide, it is limited tribochemical reactions and more of tribomechanical wear with grain boundary cracking, localized spalling as the major wear mechanism. Zirconia, it is the transformation induced cracking in, and if you remember correctly, in case of zirconia I have shown that tetragonal zirconia undergoes phase transformation to orthorhombic zirconia during the cryogenic sliding conditions. And the reason that I have provided while explaining these intriguing observations was that tetragonal zirconia to monoclinic zirconia, this particular transformation, that one is the intermediate product, that is orthorhombic zirconia. Since we are doing these experiments for relatively shorter time, 10 minutes or so, we are giving the system, we are not giving enough time to the system to come back to the equilibrium transformation phase, that is the monoclinic zirconia and therefore orthorhombic zirconia forms. And in case of the alumina, what happens it is that thermal conductivity effect is also very important, and we have seen the occurrence of both intergranular and transgranular fracture, cleavage steps and so on, and that leads to wear of self-melted alumina as well. So, these are the conclusions. This is that high speed ball and disc tribometer has been used, and this has been designed, fabricated, and this performance has been tested to study the sliding wear of self-melted alumina, self-melted zirconia and self-melted silicon carbide. And self-melted alumina exhibits the lowest COF primarily due to 3 body abrasion. Highest COF of 0.5 is observed for self-melted zirconia. Again, it is extensive thermal induced fracture, severe microcracking, and cleavage fracture dominates the wear of self-melted alumina or zirconia. And this is the kind of key summary on this cryogenic wear of ceramics. And then what we call is that new findings, like under high speed sliding conditions, coefficient of friction of self-melted alumina in liquid nitrogen is lower due to 3 body abrasion, and for the first time we have reported, I think it was in American Ceramic Society journal, that tetragonal zircon to orthorhombic zirconia phase transformation can take place under cryogenic sliding conditions. And if you remember correctly, that one of the intriguing observations was the fish scale microcracking pattern which was observed for self-melted zirconia. So, this is the summary of the cryogenic wear of materials in. So, what we have observed, that the differences in the wear mechanism can be attributed to a host of factors, and those include the cryocooling effect and faster heat dissipation. Second one is a brittle fracture enhancement and phase transformation and unique cracking characteristics. Third one in the changes in the mechanical property and surface hardening. And fourth one, in case of silicon carbide, it is a limited tribochemical wear for metals or non-oxide ceramics, that is silicon carbide. Okay. So, with this I close this all these lectures on the cryogenic sliding wear of materials, and then I will now start with this wear of the high temperature ceramics. Thank you.